This is the last video about rotation. It consists essentially of one rather difficult example using conservation of angular momentum. And this is also problem 50 in your textbook, chapter 12. There's a diagram there, but essentially you have a uniform thin rod. You're given length and mass. It has a pivot about its center, and it's sitting at rest, and it's on a frictionless plane, so no torques. And it gets hit on one end by a bullet moving with speed v. And the angle that the bullet makes with the rod is 60 degrees. And we want to find, and we're told that after the collision, the rod-bullet system is rotating with a speed of 10 radians per second. And we want to use that to find out what the original speed of the bullet was. Now we're going to use conservation of momentum because there's no torque about that pivot. But because there will be a force at that pivot, we're going to have to use that pivot as the point about which angular momentum is conserved. So we'll say that the initial angular momentum is just the angular momentum of the bullet. And that is equal to the mass of the bullet times the velocities of the bullet times L over 2, because that's the distance r, times the sine of 60 degrees. Now the problem is we don't know v, that's what we're looking for. So what we have to do is find out what the angular momentum is after the collision, and then use that to figure out what the velocity is. So after the collision, the angular momentum of the rod is I omega. That's easy enough. And the angular momentum of the bullet is its mass times its final speed after the collision, because notice as the rod starts rotating, the bullet's still moving, just not nearly as fast as it was before. And that's times L over 2. But because the bullet is stuck in the rod, we can say that the bullet's speed after impact is omega L over 2. We can also say, looking on page 227, that the moment of inertia for a rod rotating about its center, is 1/12 ml squared. And so this means that the angular momentum is 1/12 ml squared omega plus m L squared over 4 omega. And we know all the quantities in that, so we'll go ahead and get a number for L, and that will be 0.835 kilogram meters squared per second. And now conservation of angular momentum tells us that that is equal to the initial angular momentum. So 0.835 equals mv L over 2 sine 60 degrees. And a bit of algebra gives us v equals 2 times 0.835 over ml sine 60 degrees. And the initial speed of the bullet was 1,286 meters per second. Now that problem, although I told you it was nasty, is not actually that bad. It looks scary because conservation of angular momentum is a new topic, but it really wasn't that bad. Now what will make this more complicated is, let's say the rod were sitting on ice rather than held by a pivot. Now that's very interesting because now there's no longer a pivot. So the bullet comes in, hits the stick, and the stick does start rotating just like before. If there's no pivot pin in here, there's, no torque. So angular momentum is conserved. But now, because there's no pivot, that also means that there are no horizontal forces on it, on the system. And if you recall back from several chapters ago, if there are no forces that act on a system, then its linear momentum will also be conserved. So in the previous example, angular momentum was conserved, which meant that the rod started rotating. Now here, linear momentum is conserved as well. So the whole thing is going to start moving in the original direction of travel of the bullet while spinning. So it'll start spinning and moving. And to calculate the angular speed, you'd use conservation of momentum, or conservation of angular momentum. So how fast it ends up spinning. And you would also use conservation of linear momentum to find the final velocity of the center of mass. So conservation of linear momentum tells you the velocity of the center of mass. Conservation of angular momentum tells you the angular speed about the center of mass. So again, it's translation plus rotation. Now the next question is energy conserved? And the answer to that is no. It is not conserved, and the reason why would be that when the bullet embeds itself in the stick, it breaks part of the stick, and that does work, and so energy is not conserved. Although you will find that less energy is lost in the case where there's no pivot than in the case where there is a pivot. Why that is something we'll get into in a nice little AP practice problem that we'll work in class at some point in the very near future. This is the last video for rotation. We have one more unit to cover in mechanics, and that is gravity, where we'll tie almost everything in mechanics together, and then we'll move on to electrostatics, which is a lot of fun.